Going to be my report on the Physics 2211 lab number 1. So what's the purpose of this particular lab? So the purpose we are looking at today is we're studying how a constant velocity varies between a real-life model and an online model. So obviously in real life it's going to be a little bit different because we can't really truly capture constant velocity unless there are no frictional forces acting on the ball, which is going to be my object of choice, is going to be a lacrosse ball. Um, so really the only way to achieve constant velocity is if we were to put it out in like the middle of space or something like that where there's nothing acting, any forces on the object. And then obviously in the model, we can just say that there's going to be no net force acting on the ball, and we'll see what really happens if there was true constant velocity. And so the physics concept we're looking at today is Newton's second law, which is F equals ma. So what are the system and the surroundings? So the system is, like I said a minute ago, was the lacrosse ball. The surroundings, basically it's going to be everything else. So everything else is going to be acting a force on the ball. So that includes the ground, so that's going to be friction. The air is going to be air resistance. And then earth is going to be gravity. So stuff like that. So our system in this particular lab is just the ball. Okay, so what are the initial conditions? So the initial conditions are that the net force on the ball is equal to 0. And then the initial velocity that I calculated was about 0.909 meters per second. And the total track is around a meter long. It's going to be a little bit longer than that, but just around there. Okay, so the main physics concepts we're looking at today is, like I said earlier, F equals ma. So obviously here we're looking at if F net was going to be 0, so that means there's going to be 0 acceleration on the ball. But obviously we'll see in a second that in real life that's not so much the case, and there's actually going to be a little bit of friction slowing it down. And we're also going to be seeing that the initial velocity is going to be equal to the final velocity. Okay, so let's look at a real life example. So as you can see, we have the lacrosse ball here. It's a pretty smooth, hard ball, so there's not going to be too much slowing down, as well as the floor is also, there's not much friction coming from the floor. As you can see, the line here is pretty straight, which means our velocity is almost pretty much near constant the entire time, just because this is such a short time clip. We can't really capture the ball slowing down too much, but we do see here at the end it kind of starts to curve off just a little bit. So we'll see the initial slowing down right there at the end. And that's really going to be the difference between this and the glow script model. So let's take a look at that now. So here's all my code for this. So the ball's mass, if you were wondering, was 0.149 grams. 0.149 kilograms. And then the initial position is going to be 0. And the velocity, like I said earlier, is 0.909. There's some more stuff there, but, you know, for the sake of simplicity, we'll say it was 0.909. And then the timestamp is going to be 0.033 seconds long. And the way I calculated the position was I added the position and then I added the velocity times the delta time at each timestamp, basically, to update position. And then velocity just stays the same, so that, you know, adding 0 to that. And then, as you can see, F net is set to 0. So look at this graph. It's pretty straight, you know, no curving. So this is what would happen if in an ideal world where there was no forces acting on the ball. So I laid them over each other here in this little Excel model, and they're honestly almost perfectly on top of each other, which is kind of not a great example for the video, but the time of the video was just so short that there couldn't be much of a discrepancy. But you can see it kind of starts to dip under there at the end. So if the video was a little bit longer, I believe that the observed would kind of curve out and flatten out. Okay, so what if the axes were flipped? The velocity would remain constant, and they would have the exact same magnitude, which means the results would really just remain the exact same. Um, and then, so what does this all mean? So my real life observation was very close, as we saw. It does not mean there's zero net force in the real life observation. It just means that we didn't have enough time to see the force of friction and air resistance acting on it enough. Yeah, so it's slowing down due to friction and air resistance. And yeah, if the real life observation truly had zero net force, there would need to be a push force that kind of equals the friction and the air resistance so we could actually achieve a net force of zero. And that's all I have for you guys today. Thank you so much.